All right, welcome to lesson 5.04. Here we're going to work on writing an exponential function if we're given a table of values or a graph of the function. So to help discover this process, I want you to try a pretty simple one on your own. So the graph of an exponential function of the form y equals a times b to the x is shown below. Here it is. Find the values of a and b. And I want you to explain your process. So go ahead and copy this out, and I'm going to give you one little hint, which is to think back to the example of the rice on the chessboard. Think about what type of change was occurring to the rice and how that was shown in the function that we wrote to model the number of grains of rice, and that will hopefully help you with this one here. Go ahead and try this on your own, and then press play, and we'll take a look at it together. Okay, so the key to this question is recognizing that we have an exponential function, y equals a times b to the x. Now, the example that we keep coming back to with the grains of rice is very helpful. In that situation, we were doubling the number of grains of rice every square. And because of that, we needed a function of 2 to the x, so that every time x increased by 1, we would multiply by another value of 2. So what we need to look at here is what type of a function do we have? Do we have an exponential growth or an exponential decay? And then if we can determine how it's growing or how it's decaying, we'll know what the base should be. So let's take a look here. This is clearly an exponentially decaying function. And we can see a couple of points here. So for example, at 0, the value of our function is 1. And then at 1, the value of the function appears to be at a half. At 2, the value of the function appears to be at a fourth, and so on and so forth. And so I can see here that the pattern it's following is one of being cut in half. The value is being cut in half, which means that every time x increases by 1, we're going to multiply by 1/2, meaning that my base, or the value of b, will be 1/2. The value of a is then pretty easy to find. So at this point, I have the function y equals a times 1/2 to the x. Notice here that I can see very clearly that when x is 0, the value of my function is 1. And when x is 0, this whole piece here is going to be 0 because 1/2 to the 0 is 0, which means that a will have to be 1 because y is 1. In other words, it's the y-intercept. So my function is going to be y equals 1/2 to the x, or in other words, a function that models exponential decay where my value is being cut in half. All right, so notice that we can do this regardless of the graph that we have. We can go ahead and figure out what that base should be, and then we can find out what our y-intercept or our leading coefficient needs to be as well. So let's go ahead and copy down a couple of notes here to make sure we have some reference. Okay, so the key points that we went through there in that example were, first and foremost, determine whether my function is exponentially growing or decaying. This way I have an idea of what sort of b value I'm dealing with. I knew I had exponential decay, so I was expecting a b value between 0 and 1. Now a little bit of new vocabulary here, the base, which we can also call the growth factor, or if we're decaying, the decay factor. And we want to find this base by identifying the multiplicative rate of change. Okay, what do I mean by that? We were looking for what I'm multiplying each time to go from one value to the next. And we'll see a great example of this in a second. So what I want you to do is really pay attention to how we do that, and that will allow you to make some extra notes for multiplicative rate of change to help you out when you're doing this on your own. Then we want to find the y-intercept, or we can use any other point that we have to solve for our leading coefficient a, just like we did in the first example. In fact, we were able to do that in our head. So let's take a look at an example here. I want you to go ahead and copy this down and try and go through steps 1 and 2 on your own first. Okay, so if we look at this example here, we'll notice that we're dealing with exponential growth because as x increases, so does the y value. Next, we need to decide what our growth factor is going to be. In other words, what would we multiply by every time that x increases by 1? What is that base value going to be? The only issue is here that when I look at this table, I don't see an increase of 1 in the x direction, right? I see rather an increase of 2, right? So there's an increase of 1, and another increase of 1 gives me a total increase of 2. So I can't quite decide what I would need to multiply by to go from 0.5 to the mystery number in between. All I can do is ask myself, what would I need to multiply 0.5 by to get 4.5? So an easy way to do that is to take 4.5 and divide it by 0.5, or you might notice that 0.5 times 9 is going to give me 4.5. So let's go ahead and note that here. But we also are not looking for what we need to multiply by over a step of 2 in the x direction. We'd like to know what we need to multiply by each step of 1. So we kind of want to break this up into 2 steps. And note that what I'm going to do is I'm going to multiply by something once, then I'm going to multiply by it again, and that's going to result in a multiplication by 9. So ask yourself, what could I multiply by twice that is the same as multiplying by 9? Not too tricky. Multiply by 3 twice is the same as multiplying by 9, because 3 times 3 is 9. And you can see that this works. 0.5 times 3 is going to give me 1.5. 1.5 times 3 is going to give me 4.5. So I can sort of fill in that missing spot. So I know that b is equal to 3. Okay. Now, at this point, that means I have the equation y is equal to a times 3 to the x. So now I need to figure out what a is, and luckily I have the y-intercept. In other words, when x is 0, y is 0.5. And I can see really clearly here that when x is 0, right, 3 to the 0 is 1, and so I'd have a is equal to whatever y is. Y is 0.5, so a is 0.5. Now I want to point out that I didn't have to use the y-intercept. I could have used another point. So I could have plugged in the point 4, 40.5 for x and y respectively, and still solved for a. You can do that, it's just a little more work. Using the y-intercept makes it easy, because when x is 0, that usually results in me taking my base and raising it to the 0 power, which is always 1. So a is equal to 0.5. And that means that my equation is y equals 0.5 times 3 to the x. Like that. All right, I'm going to give you a couple problems to try out on your own. All right, here are a couple of problems for you to try on your own. I made them semi-challenging on purpose. I want you to spend some time with these here. For number 1, I would recommend sketching a quick graph so that you get a visual representation. And for both of these, make sure you think about what it is you want to do. What are you going to find, and what's your plan for finding them? And only then should you go and execute your plan. It also might be helpful to go back and review the example that we just did so that you can get a really clear understanding of how we find the multiplicative rate of change.